Hi, my name is Michelle Post, and my share time is about the independent t-test. And we'll start by talking about the purpose of the independent t-test, which is to test the difference between two independent means. What we do is we take data from two separate samples. So, for example, we can have a sample of men versus a sample of women and compare their means, or we might have a sample of students taught using a particular method versus students using another method and compare their means. If you recall our homework assignment, we actually each got a test that we were looking at, and we were comparing the scores of the men versus the scores of the women, and we used our independent t-test for that. Try not to confuse that with taking two sets of data from the same sample. An example of that would be taking one set of scores before therapy or treatment and comparing that to the same set of individuals after they've experienced the therapy or the treatment. That would not be something that we would use the independent t-test for. We actually call that a repeated measures or within subjects type analysis, and it's a different statistical analysis altogether. So we'll go ahead and just remove that and start with a good definition of our independent t-test. So it's a research design that uses a separate sample for each treatment condition or for each population, and it's called an independent measures research design or a between subjects design. The assumptions, the first one is that each sample is a random subset of the represented population. So what that looks like is, for instance, if I have a population of men and women, each of those would have a mean, but because they're so large, it would be almost impossible to actually calculate the mean of these populations. So we would take random samples from each population, and those are nice to work with, and we could actually calculate the means. You'll see the scores that I have up there, and those are scores that I got from my homework assignment. I thought, since all of us are familiar with that would be a nice way to kind of relate this share time to something that we already know. So I have asterisks by the scores that I got from my homework assignments. The second assumption talks about the observations within each sample, that they must be independent. What that means is, if you were, let's say, tossing a coin 10 times, and you toss it once, twice, the third time, by the time you toss it the fourth time, there shouldn't be any reason that the first three tosses would influence the result of the fourth toss or any toss thereafter, because they're independent. So a counter example would be, let's say if you gave an oral exam to 5 of your students, but you let them all stay in the same room, and the 4 of them heard the first person give the answer, well, that answer would certainly influence the answers of the other 4, whether it's positive or negative. So that would not be independent. When we go back to our homework assignment, then those were independent. We assume that they weren't cheating or working together, but that each person would take their individual exam, and their score would not affect the score of another person. Okay, the third assumption is that the two populations from which the samples are selected must be normally distributed. So I put some normal signs in there so that you could see that they're supposed to be normal. Again, because the populations are so big, we can't really measure normality, but if our sample sizes are large enough, we can certainly measure them for normality, and then make the assumption that that means they came from normal populations. We would measure those normalities by looking at the skewness, the kurtosis, the QQ plots, the histograms, and so on and so forth. And the fourth assumption says that the two populations from which the samples are selected must have equal variances, or homogeneity of variance, and we remember that from our homework as well. Let's get our head back in variances again. It just means you take each data point and you see how far it is from the mean. You're going to have some that are negative, some that are positive, depending on which side of the mean they fall. So we square them all to make them positive and add them up, and that gives us our variance. So I've put the scores that I got for variance from my homework assignments under each of these samples, and you can see that they're pretty close together, and that's what we're looking for, is that homogeneity. And again, if our sample sizes are large enough, then we can make the assumption that the populations had homogeneity of variances as well. Now, in our homework assignment, our SPSS used the Levene's test to check for homogeneity of variance, and it gave us a nice little chart. And if it did have homogeneity, then we would use that top row and use the data there, and if it didn't, then we would use the data from the bottom row. Just a note that the independent variable on an independent t-test should be nominally scaled, and again ours was with male and female, and that the dependent variable is continuously scaled, and ours again was with the test scores. The hypothesis, you would start with your null hypothesis, which speaks to the 0 or the nothing, and it says that the mu1 minus mu2 equals 0, or mu1 equals mu2. In other words, the means of the populations we're saying should be the same, so therefore their difference would be 0. Then the alternative hypothesis is the opposite, which says mu1 minus mu2 does not equal 0, or mu sub 1 does not equal mu sub 2. So we're saying that their means are not the same. Before we do any analysis, of course, we're going to set the alpha, and in this case we set it to 0.05, which is basically the separation between what should be statistically significant and what should not be. The basic structure of the t-test is the sample statistic minus the hypothesized population parameter over the estimated standard error. But that's for a single sample, and in our case we have 2 samples, so it kind of doubles the work. We basically get the difference between the sample means minus the difference between the population means, and we divide that by the estimated standard error of the difference of the sample means. Mathematically, this looks like m sub 1 minus m sub 2, because that's the difference of the samples, minus mu sub 1 minus mu sub 2, the difference of the population, over, again, this estimated standard error of the difference of the sample means. But in our null hypotheses, we said that mu sub 1 minus mu sub 2 equals 0, so it simplifies our fraction to just m sub 1 minus m sub 2 over the actual calculation for the estimated standard error of the difference of the sample means, where you'll notice that we actually use our variances and our sample sizes in order to calculate that. But unfortunately, we did not get to calculate that on our homework because SPSS did it for us, and mine happened to be 0.826. So in our final reporting, using APA style, basically you would say something like the men scored higher, give the mean and standard deviation, than the women, mean and standard deviation. This difference was not statistically significant because T with a degree of freedom of 98 was 0.826, and of course SPS gave me my P, my probability, which was 0.411, which was not less than the 0.05, which would have made it statistically significant. My Cohen's D was 0.17, which of course speaks to the effect size. And finally, we want to address the null hypothesis, which says we would fail to reject the null hypothesis, which stated that the means are the same, and that's because our P was not less than 0.05. So that's all I have. I'm sorry I went over in time. That was kind of a lot to squeeze in. These are my references, and if you look on the discussion page, you should see the handout as well as some links to some websites that talk about the independent t-test. Thank you.